Way back in the middle of World War II, scientists unlocked a power that was hidden deep inside the atom itself. They created the world's very first controlled nuclear chain reaction, and with it came this incredible promise of a clean, almost endless supply of electricity for the entire planet. But, as we're going to see, that promise came with some serious strings attached, ones we're still trying to untangle today.
I mean, the potential is just staggering. If you take just 1 kilogram of nuclear fuel, that's about the weight of a pineapple. A modern reactor can churn out enough electricity to power an average American home for almost 34 years. It's a mind-boggling amount of energy from such a tiny amount of stuff.
But here's the strange part. Even with all that incredible potential, nuclear power is actually on the decline. You can see it right here. It peaked way back in 1996 when it was making almost 18% of the world's electricity. Today, that's dropped all the way down to just 11%. And it looks like it's going to keep on falling. So that really brings us to the big question we're tackling in this explainer. What happened? Why didn't this amazing technology completely take over our power grid? To really get that, we need to first dive into how it works, and then we have to look at the really unique and really difficult challenges that come along with it. Okay, so it all starts at the atomic level. The whole secret to nuclear power is splitting a very specific kind of atom, uranium. When you do that, you unleash this massive force that holds the atom's core together.
This process is called nuclear fission, and it's pretty simple, really. You're just cracking open the nucleus of an atom. When that happens, a tiny, tiny bit of its mass gets converted into a huge amount of energy. And that one simple reaction is what powers every single nuclear reactor on the planet.
But here's the thing. Not all uranium atoms are created equal. See, most of the uranium you dig up is this stuff called U-238. Which is pretty stable. The magic ingredient, the one we really need, is its super rare cousin, U-235. Think of U-235 as the spark plug. It's way less stable and it splits apart really easily, which is exactly what we need to get this whole party started. So how do you get from one little split to millions? Well, it all comes down to a chain reaction. Picture this. A single neutron hits a U-235 atom. Boom! It splits, releasing a burst of energy, but it also releases 2 or 3 new neutrons. And those new neutrons, they shoot off and hit more U-235 atoms. And the process repeats, growing bigger and bigger and bigger, all on its own. Now, if you let that chain reaction run wild, that's a bomb. So really, the entire job of a nuclear power plant is to figure out how to tame that incredible power, to control it perfectly so it releases its energy slowly and steadily. And all of that happens inside the reactor core.
So, how do they do it? Well, a reactor has 3 main parts to keep things in check. First, of course, you've got the uranium fuel. Next up is something called a moderator, which is usually just plain old water. Its job is to slow those neutrons down so they're more likely to hit another atom. And the last piece of the puzzle is the control rods. These are basically the brakes, made of materials that just soak up any extra neutrons to stop the reaction from getting out of hand.
So by moving these control rods in and out, operators can basically hit the gas or the brakes on that chain reaction, keeping it perfectly balanced. And when it's balanced like that, the reactor can pump out a steady, massive amount of heat and electricity nonstop for years at a time. This is the dream of nuclear power in action. But, and this is a big but, this is where we run into our first huge problem. The uranium you dig out of the ground isn't actually ready to go. You have to process it first, and that process is, well, pretty risky. The issue is the neutrons flying around are just moving too fast. To make the chain reaction actually work reliably, you need to up the odds of them hitting their target. And the way you do that is by increasing the concentration of that key ingredient, U-235. That whole process is called enrichment. And this is where things get really tricky. So, natural uranium, it's less than 1% U-235. For a power plant, you only need to enrich it to about 4%. But here's the kicker. If you just keep that exact same process going, you can enrich it all the way up to 90%. And that, well, that's weapons-grade material. So yeah, the tech you use to make clean energy is almost identical to the tech you use to make a bomb. And that's exactly why these enrichment facilities are watched like a hawk. It's a huge international security issue, and it's really the first big shadow that falls over the promise of nuclear power. Okay, so that's the fuel. The second huge challenge is the reactor itself. And specifically, what happens when all of that careful control that we just talked about is suddenly and catastrophically just gone? First, a quick refresher on how it actually makes electricity.
The fission reaction gets incredibly hot, so you pump water through the reactor core to soak up all that heat. That super hot water then boils a different tank of water, creating steam. The steam spins a turbine, and voila, you get electricity. Simple enough, right? But the key to the whole thing is that you can never, ever lose that constant flow of cooling water.
Because the meltdown is exactly what happens when the coolant stops flowing. Maybe a pipe breaks, maybe the pumps fail, but without that water, the heat has nowhere to go. The fuel starts to get hotter and hotter until it literally melts. And as it melts, it releases this terrifying cloud of radioactive gas, and the pressure inside the reactor just starts building and building.
And that brings us to the last line of defense. This huge building made of steel and reinforced concrete. Its only job is to contain all that radioactive horror. But if the pressure inside gets to be too much, the building can break. And then all of that radioactive material escapes into the atmosphere, free to travel wherever the wind takes it.
But let's say our reactor runs perfectly its entire life, no accidents. We still have one massive, maybe even unsolvable problem. What do you do with the waste? Because once the fuel is spent, it can't make power anymore. But man, is it dangerous.
They call it spent fuel. And it's basically this toxic cocktail of stuff. Leftover uranium, other radioactive bits and pieces, and this brand new man-made element called plutonium that actually gets created inside the reactor during the whole process. And this waste is a double whammy of bad news. First, you've got the environmental risk. It's so intensely radioactive that you have to lock it away from everything and everyone for tens of thousands of years. And second, there's the security risk. You can actually pull that plutonium out of the waste and use it to make nuclear bombs.
And to really wrap your head around how long we're talking, plutonium has a half-life of 24,000 years. That means in 24,000 years, it will only be half as radioactive as it is today. I mean, look at this timeline. The entire history of human civilization, from building the pyramids to right now, is just a tiny blip compared to how long this stuff stays dangerous. So, what are we doing with this forever waste? Well, right now, pretty much nothing. There isn't a single permanent storage site built anywhere on the planet. So most power plants are just storing it on site, indefinitely, basically kicking this incredibly dangerous can down the road for countless future generations to deal with.
And that brings us full circle. On one hand, you've got this incredible source of power. But on the other, you have these challenges that are just on a scale we've never dealt with before. The risk of weapons, the fear of a meltdown, and this waste that will literally outlive our civilization. So what do you think? Is nuclear energy a powerful solution we need for the future, or is it a permanent problem we've already created?